Hello and welcome to day 18, last day of formal proof, where we'll be doing our second case study, this time on edit distance. So you'll want to recall that from day 9, the type edit, where we talked about the ways you might compute similarity between one strand of DNA and another. And the approach we took was, well, think of the edits that it would take to get from one to the other using some notion of edit, copy, add, delete, substitute. Um, and the fewer edits we have to use, or the cheaper edits we have to use, the lowest cost edits we have to use, the more similar the two strings are. So to get from a strand to itself, there's no edits necessary at all, so it's cost 0. If only one thing changes, maybe it'll be just cost 1, and so on. So the lower the cost, the more similar. This was the idea. We spent a bunch of time writing edit generating functions, which took a pair of strands and produced some set of edits, some list of edits. With the ultimate sort of achievement being Levenstein's edit distance, which we made a claim was optimal. We said, hey, this is the best that you can do. So what we're going to do today in day 18 is formalize that claim. We're going to make it clear what we meant by optimal, clear what we meant by saying our programs were correct, and prove it. So I've got the little plan for the day over here. We're going to start just with a little recap, just looking at our definitions, and then we'll talk about basic validity / correctness proofs, talk about Levenstein's correctness proofs, do a minor detour to talk about a function that just computes distance, which on some level is all we really care about, and then we'll talk about optimality. All right, so let's get started. I hope you like the new Emacs theme. If you don't, let me know, though after these 5 videos, I don't think we'll be seeing too much more of Emacs in any case. Okay, let's get started. So, I just want to begin with a recap of our various edit generating functions. So delete edit is not yet an edit generating function. I mean, it produces a list of edits, but I mean something particular by that. Delete edit says you give me a source strand and I'll give you the edits that get you to the empty strand. Add edit does sort of the converse. You give me a target strand, I'll give you edits that get to that strand from the empty strand. Delete add edit, this is what I would call an edit generating function, in the sense that you really give it 2 strands, some source strand, some target strand, and it produces the edits that it would take to get from source to target. I mean, it produces some set of edits, list of edits, sorry. Not a good one, right? It doesn't even look at them. It just says, well, delete everything in source and then add everything in target. It could go the other way. It doesn't really matter. This is the one that we came up with. So this is sort of the simplest correct edit producing function we could come up with, right? It's not going to produce low-cost edits in particular. Here we are, right? It's a definition you can have. Here's one that's new that we'll be doing proofs about because we'll need it later, particularly when talking about optimality. So this is like delete and add edit. It basically is the set of edits that says, oh, yeah, these are the edits that take a strand to itself. So ultimately, these should be 0 cost. Now, we could safely, if you remember the definition of edits, we could safely have this just be empty list, but it's nicer to have it be clear that it's just copy. Okay. We wrote some more interesting ones. So here's one that we gave to you, naive subedit, which says walk down the 2 lists of the 2 strands, the 2 lists of bases, and then just substitute in whatever the target strand has. Right, and this will do better than delete add edit. This will be lower cost in general. We had you write subedit, which is even better than naive subedit because sometimes you can copy. Right, if the bases on the 2 strands align as you're marching your way down, then you can just copy, and you'll have an even cheaper list of edits. So that's another one we defined. Okay, Levenstein is the last one here, and it is the best, right? We're going to prove, actually, that you can't do better than Levenstein for this notion of edits. Your definition maybe didn't look exactly like this. Here's what we wrote. The general gist of it is you compute 3 possibilities. One sort of in the naive subedit, or excuse me, the subedit mode. One doing a delete and one doing an add. And each of these kind of shifts around what you continue with in your recursive call, right? Each one consumes a different number of bases from the 2 strands. And then the key idea in Levenstein is that we say, well, just choose the best one. Choose whichever one looks best. Okay. So I wanted to get all these definitions sort of settled so that we're all proving things about the same definitions. In the next video, we'll start going over what do the proofs of correctness for these look like. Talk to you soon.